Hey everyone, hope you're doing well, and we're going to be continuing our understanding here in drawing force diagrams for a body going down a ramp with friction. Now in the last video we actually looked at doing this for an object that was in motion. That is, the net force was not zero and therefore the block was going down a ramp. Well, here it's going to be not moving, it's going to be stationary. So let's just do this again, and remember that when you do this, and I encourage you to do this at home, that you're using colors, that you're articulating what you're knowing, you're drawing things, you're writing on your whiteboard, and you're explaining what's going on. That way it's going to get stuck into your head. All right, so let's get into this one here. So if we just enlarge this diagram here, and now we're going to go over all these forces. This is with friction and it's not moving, okay? All right, so let's have a look here. So we've got our, and let's just choose our colors. So here we have the center of mass, and that is of course going to have our pull of gravity going downwards. It's going to have a gravitational force, so we could call it the weight force, right? This keeps moving around my hand, so we have Fg, and that is equal to mg, okay? And of course that's the weight force, because weight is exactly the same. Weight is equal to your mass times gravity. Okay, so let's just call that from the weight force right now. But then we said we have a coordinate system. That coordinate system was vertical and horizontal. X was this way, y was this way. Okay, and we said that in the last example we said going down the slope was positive, right? Because there was actually movement going down the slope. Here it's stationary, so we could choose any way as positive. I'm going to choose going up the slope as positive, because just normally with our coordinate systems towards the right is positive. So if we've got our force going down, let's do our normal force, which is going up. Okay, remember our normal force is perpendicular to the surface that we're on. So there's our normal force there. And of course we have to have our forces in the same orientation, or our same coordinate system. So now I'm going to break my weight force up into the vertical component. Okay, and of course that there is called Fg perpendicular, and if we're talking about this angle here, which is the same as this angle here, then that's going to be mg cos theta. Okay, right, and then of course if we just change our color again, we've got our blue force going that way, and that is Fg parallel, and that is mg sine theta. So we have our two components now of our weight force done, and of course now they're all acting in the correct direction here. So we've got the horizontal component of our weight force acting down the slope, but since it's not moving, it must therefore have a force going upwards, and of course that is the weight force. That is the frictional force. Okay, so if I now do all of my forces into a single diagram, let's put one over here. Okay, so let's get our green back. So we had our normal force going up. We had our mg cos theta going down. We have our force of friction going that way. And then we had our blue force, and that was our mg sine theta. And notice in this time here, my horizontal components are exactly the same length, so therefore they're equal and opposite, therefore the object is not going anywhere, as builders like to say. So that object is just stationary on there. Now, to reinforce this connection to Newton's first law and second law according to the syllabus, well, this object is agreeing with Newton's first law, because Newton's first law says that objects at rest stay at rest, or if they're in motion, they stay in motion at a constant velocity in a straight line, unless acted upon by an unbalanced external force. Well, this is at rest. It's not going anywhere because there is no unbalanced force. The forces are balanced. How can we show that? Well, of course, with Newton's second law, right? Remember, Newton's second law says F, the sum of the forces, equals ma. Well, let's look at the sum of the forces in the vertical direction. Okay, so this is the y direction, and so therefore the sum of the forces in the y direction is the force going up, which is the normal force, Fn, right? And we're going to plus that to the other force in the vertical direction, which is what? It's actually the vertical component of our gravitational force, so that's Fg parallel. Now when I do that, I should actually, of course, include the direction, so it's plus, whoops, sorry about that. It's plus, and then we've got the minus Fg parallel, because remember, if up is positive, downwards is minus. Okay, so now if I go Fy equals Fn plus, whoops, Fn minus Fg parallel, and if it's not moving, right, if it's not moving, that means the sum of the forces in the y directions is 0, right, because there's no net force, Fn minus Fg parallel. And then if I rearrange this around, so I've got Fg parallel equals Fn, they're both equal to each other in terms of magnitude, they're opposite in direction, and so if they're both equal and they're opposite, then of course there's no motion there. And I could put that in a bit more detail if I wanted to, because we know that Fg parallel is equal to mg cos theta, so I could go mg cos theta equals equals Fn. Okay, and depending upon what the question is, you could find out an unknown there, right? So they might say to you, this is the case, this is the mass of the object, what is the angle at which in which it won't move, and then you could find the angle, etc. So that's just a little bit of proof that the vertical forces are equal and opposite using Newton's first and second laws, and we could do the same thing, of course, with Newton's with the horizontal force as well. But since both of them are net force is equal to 0, that means, of course, it's not going anywhere, the object is stationary. So to finish this little video off, right, remember we have talked about friction. We've labelled forces with friction. We've talked about static friction. Static friction is the maximum force that an object can have until it just starts to move. Okay, remember that friction force acts opposite to the applied force. And so if I've got a force going down that way, then I have to have the frictional force going backwards, and if these are equal and opposite, then there is no motion. So the sum of the forces, right, the net force is equal to 0 newtons, and the object is at rest in this instance. If it's traveling down a slope, or if it's going on the highway at a constant velocity, I can still have the net force equaling 0. It just means it's maintaining at that constant velocity. It's not speeding up, it's not slowing down. Then we can have sliding friction or kinetic friction, okay, and that of course is the friction, it acts opposite to the direction of motion, but it's also, it's friction that's occurring as you're sliding across another object. And then you can have rolling friction as well, the point at which you're contacting the ground, you'll have some friction at that point there, and that's called rolling friction. So they're the 3 different types of frictions. We've learnt in this video how to draw our diagrams for an object on a ramp in terms of no friction. We combine that with our understanding in the previous video to do with friction. That gives you a good basis to do some problem solving and do some questions, which we will do in the next video. So as always, make sure your diagrams are detailed. You can draw them down, you're using colour to enhance your memory. You're of course articulating it and describing it and explaining it to a friend, maybe even to your pet gecko in your room, because it's how we learn, both kinesthetic, using your hands, visual and auditory, that really solidifies this information, and that you can link it to the syllabus dot points as well. So I hope that makes sense to you. I'll see you in the next video.